Okay, in this discussion, we're going to talk about the chain rule. In order to talk about the chain rule, we have to know what a composite function is. So let me make a note here that the chain rule is going to be used to differentiate composite functions. Okay, we are going to use the chain rule to differentiate composite functions. All right, what is a composite function? Well, we're going to call a composite function, let's call it M, if it looks like the following. So a function M is a composite function if M of x is defined as f of g of x. Okay? And we have here that g of x is what we'd call like the inside function. Okay, let's practice function composition. Another way that you would see this written would be that M could be defined as f composite g. That's a little circle here that represents function composition, not to be confused with multiplication. So let's just see if we can understand what function composition is. Let's suppose, for the sake of being able to discuss this, that f of x is defined as 2x minus 1, and g of x is defined as, how about the square root of 3x plus 5. And so let's say that we're going to find f composite g. That's what we're asked to do. Okay, so the definition, f composite g, as we showed above, is the same thing as saying find f of g of x. And so let's consider this. When you think about order of operations, you think about parentheses and go work from the inside out. So let's just kind of use that same logic. We're going to work from the inside out. And so we should be used to function notation. And what I'm going to do is I'm going to highlight here g of x and work from the inside out. That's g of x. And so I'm going to use the fact that we've got equality here. And I'm going to say, well, this is the same thing. Let's leave the outside here as f of, and let's replace g of x with its equivalent, which is the square root of 3x plus 5. And now that I see it written in this manner, this is saying everywhere that I have an x in my function f, so let's change color here, everywhere there's an x in the function f, it will be replaced by what's in parentheses. And that's what this function notation says we're going to do. And so it turns out that if I go back up to f, it says it's twice x, but again, x is going to be replaced by this square root of 3x plus 5. And then it says I subtract 1. So all I've done is I've replaced where x is with this 3x plus 5, square root of that rather. Okay, and then if I can actually go further with this and simplify, I would do so, but it doesn't look like there's anything else for me to do. This would be the function composition. Okay, so let's maybe do it the other direction. Let's do a g composite f just to make sure we have the hang of this. It turns out to be something very special if part A and part B here are the same. That would mean that f and g are inverse functions. That's a whole different topic though. So I just want you to note that it's not necessarily going to be true that f composite g is the same as g composite f. That happens, but that's going to be the case when those functions are inverses. Okay, so what does this mean? It says it's g of f of x is what I'm finding. So I'm going to use this highlighter and I'm going to work from the inside out. So I know what f of x is. That's this function right here. And so I'm going to maintain that I'm taking g of f of x, but f of x is going to be replaced now by 2x minus 1, right? That's what f of x is. So I'm going to use its equivalent. And then this notation, this g of 2x minus 1, that means go to your function g, and everywhere there's an x, replace that with what's in parentheses here, 2x minus 1. So I go up to g, it says take the square root of 3 times x, but x is being replaced with 2x minus 1. And then it says to add 5, right? So I go back up, I replaced x with this 2x minus 1. And then I'll simplify if possible. So it looks like I would have, what, 6x minus 3 plus 5, all of this under the square root. And I can just combine the constants so that I have square root of 6x plus 2. So I have performed the function composition, would say in both directions here. And you can see these are two different answers. So these are not inverse functions. But that's not what we're really talking about here. We're wanting to make sure that we can understand what a composite function is. It's saying that you would have a function, maybe a typical linear function, most basic f of x equals x, and suddenly replace the x with maybe now 2x minus 1. So I can consider that to be a composite function. If I see something that's a composite function, I'm going to use what's called the chain rule. And so let's see what that means. Okay, so chain rule. It says if I have a function, let's call it y, and it's equal to a composite function, or I could identify this as a composite function, then to take the derivative of that composite function, that derivative we can call it dy dx, is going to equal, let's take the derivative of that outside function, which we're calling f. So I've got f prime of g of x. I'm rewriting that inner function, so I've taken the derivative of the outer function, rewritten the inner function, and then I multiply by the derivative of the inner function, which we're calling g. So I've got the chain rule is f prime of g of x times g prime of x. And so let me just kind of make some notes here, because again, these look great when you are just trying to use the property right in front of you, and you're able to look at the property and say, okay, let me follow the pattern. But when we walk away from our notes and we have to sit down and take an exam, for example, I need to have a good way to remember this. And so we can think of this first part as taking the derivative of the overall function, and then we multiply it by the derivative of the inside function. You can see my letters are disappearing here. I'm not quite sure what's going on. But this is going to be best demonstrated with some examples with some actual functions in it. And then, of course, you will need to practice to make sure you have this down. Okay, so we're going to take the derivative. We're going to differentiate using the chain rule. Soon I'm going to have to recognize if I'm going to use the chain rule. And let's look at example A here. It says y is going to equal the quantity x to the 4th minus 5x all raised to the 6th. So this is like me saying that we have a function. The function is like f of x equals x to the 6th. And that I replaced everywhere there's an x in the function f, I replaced it with x to the 4th minus 5x. So if you think about that, if I asked you to find f composite g, that would be doing f of g of x, as we did a moment ago, and that would be saying everywhere there's an x in f, I would replace it with the quantity x to the 4th minus 5x. And you'll see that's exactly what we've done. We've gone to this function f, and I replaced it with the quantity x to the 4th minus 5x. Okay, so this truly is a composite function. All this stuff is side work here just for me to, I guess, really prove to you that what we have in front of us is actually a composite function, and it requires chain rule, aside from the fact that it tells me to use it. Okay, so that means I'm going to take the derivative of what we call the outer function. So I look at this, and I think of this whole thing as like the outer function. And I'm going to follow this pattern I see up here. So I'm going to take the derivative of the overall function. There's nothing to rewrite as far as trying to manipulate the problem as given. So I'm going to go straight into taking the derivative, which means I'm going to write dy dx, or y prime, to show that. When I take the derivative of the overall function, just kind of look back here, what you would do is like a power rule. You would take the 6, you'd multiply it to the front. Well, this says I'm going to take the derivative of the overall function. I'm going to reduce that power by 1. And then that chain rule says, now I'm going to multiply that by the derivative of this inner function. And the derivative of that inner function is going to be 4x cubed minus 5. Okay, and then maybe the last thing I do is I shift this to the front. I say this is going to be 6 times the quantity 4x cubed minus 5. Be careful with writing down your parentheses and writing or typing in exactly what you mean. And so perhaps I can distribute the 6 into that first set of parentheses. But I need to be really, really careful on how I type that in. I can't leave off my set of parentheses. So this is me using the chain rule for this composite function. Let's try another one. Okay, so now we have example B here, and it does say at my heading I'm going to use chain rule. So we've already talked about quotient rule. You could consider using quotient rule, but this does actually say use chain rule. So to use chain rule, I'm actually going to have to rewrite so that I can use the rules of derivatives that we've talked about before in previous sections. So I'm going to rewrite this function f of x, and notice I'm denoting it as f of x because it's just being rewritten. I'm going to say this is 3 times the quantity x squared plus 4, which is raised to the negative 2. So those two things are the same thing. And now if it's rewritten in this manner, I can now take the derivative, so f prime of x, and I can use the chain rule. Remember, this constant's just going to hang out, it's going to stay with it. And so it's going to be 3 times, and then I'm going to take the derivative of the overall function. So I'm going to bring that power to the front, so I'm going to multiply by negative 2. I'm going to rewrite that inner function. I take the derivative, so I'm going to subtract 1 from this exponent, so that's going to actually give me negative 3. And then I'm going to multiply by the derivative of the inside. So I've done the derivative of the overall function. Now I multiply by the derivative of what we call the inner function here. And so the derivative of x squared is 2x, and the derivative of 4 is 0. And so as long as I can multiply these things and rewrite it in a manner that's acceptable, then this is going to look great. So I'm going to take the 2x and move it over here. So 3 times negative 2 is negative 6. Negative 6 times 2x is negative 12x. And then we have this quantity, which is raised to the negative 3rd power. And if I'd like, I can rewrite this in such a manner that I've gotten rid of that negative exponent. And so I've moved that to the denominator, and that's perfectly fine. Okay, let's take a look at another one. So we just want to get some practice in using these rules. This does say to use chain rule. So maybe I don't think this looks like a composite function. It actually is. It's like saying that I replaced the basic function square root of t. I replaced that t with 4 minus t. So this is a composite function. But to use my rules of derivatives, I'm going to have to rewrite this function, just like we did in that last one. And so I can consider this quantity, that radicand, as being raised to the 1/2 power, right? Something you take the square root of, you can raise it to the 1/2. Those are equivalent. So notice my notation. I'm still saying that I am rewriting g of t. And now that I see it in this form, I'm going to take the derivative. And so I'm denoting g prime of t then. I will use the chain rule, which says I'm going to take the derivative of the overall function. So I'll take that 1/2. I'll rewrite this inner function. I'll subtract 1 from the power, so it'd be 1/2 minus 1 is going to be a negative 1/2. And then we multiply by the derivative of the inner function. Well, the derivative of 4 is 0, and the derivative of negative t is going to be negative 1. And so we have, this could be written as negative 1/2 times the quantity 4 minus t to the negative 1/2. And then if I want to get rid of the negative exponent and maybe rewrite this in another way, I can have the negative 1, that 2's in the denominator, with this 4 minus t to the positive 1/2, since it's in the denominator. And then, of course, there are further things that I could do. So perhaps we rewrite that using the radical symbol. And perhaps from here we decide to rationalize the denominator. Okay, so these are all options we have. But what's important is right now that I can use the chain rule. I can identify when to use it, and I am able to do so. Okay, so now let's suppose that I'm taking the exam and I come across a problem and the directions say find the derivative. Okay, I've got to think about all the things that should come to mind, the derivative rules I have so far, and hopefully we're seeing this as a first function times a second function, and so we would use product rule. And so this is my first function and this is my second function. Okay, remember the product rule, we had those nice U's and V's. What I said is we could remember that as first times the derivative of the second plus the second times the derivative of the first. And so, of course, I'm referring to the first function and what's considered the second function here, these factors. Okay, so I'm going to take the derivative using the product rule. There's a little bit more to it, and we'll see that. So I'm going to take the derivative. This is dy dx then. And I go, all right, product rule says take the first, so I rewrite that first function, 3x squared, times the derivative of the second. Derivative of the second. Well, I'm going to have to use chain rule. So I'm going to take this 3, move it to the front of 5x minus 1, reduce that power by 1, so now I've got that quantity squared, and then I multiply by the derivative of the inside function. So I'm going to multiply it by 5. So here I've done the first times the derivative of the second, which involved chain rule, and now it says plus the second function, so I rewrite 5x minus 1 cubed times the derivative of the first. So the derivative of 3x squared is going to be 6x. So I've done first times the derivative of the second plus the second times the derivative of the first. Okay, so what could I do from here? Well, I'm going to highlight things that I'll multiply together. And I'm going to move maybe this quantity or this factor here to the front of that. Okay, so if I go 3x squared times 3, that's 9x squared times 5. 9 times 5 is 45, so I got 45x squared. Then I have 5x minus 1 squared. And then I've decided to move the 6x to the front of that quantity, 5x minus 1 cubed. And I can even continue from here and think about factoring out common factors if I'd like. So if I wanted to, I could factor out 5x minus 1 all squared. I could factor out, it looks like a 3x, and continue from here. So my only warning is if we get to like a multiple choice exam and you know that you've applied your product rule, and in this case within that your chain rule correctly, and you go, it doesn't quite match that final answer, you just have to be aware of what you can do to algebraically manipulate this into something that is simplified or rewritten using proper algebra. So I just want to make a note of that. Okay, so we're back again trying to find the derivative. I am looking at this, I see a quotient, so I'm going to apply quotient rule. The quotient rule, I had said we do low, d high, meaning I take the denominator, and d indicates the derivative of high, which is the numerator. So low d high minus high d low all over low low, or the denominator squared. That's a little bit easier to remember. Low d high minus high d low over low low. And now I'm going to actually do that. So I'm going to take the derivative and show with my indicator here, f prime of x, that I'm now going to take low, which is x plus 3, that quantity, and I'm going to multiply it by the derivative of the top. Okay, so be careful here, because when I take this derivative, I'm applying chain rule. So the derivative of that numerator, or d high, is going to be 3 times the quantity, 4x minus 1. I reduce the power by 1, and I multiply by the derivative of the inside. The derivative of the inside function is just 4. So I've got low d high minus high, which is the quantity 4x minus 1 all cubed, d low. So I'm going to take the derivative of the denominator. Well, the derivative of x plus 3 is just 1, and then the derivative of 3 is 0. So this is just going to be times 1. So low d high minus high d low, and don't forget to put it over the denominator squared, right? That's low low. And from this point on, it's going to be just about being able to simplify this. And so let's maybe multiply the 4 and the 3, and so I'd have 12. So I can take 12 and I can distribute it. So I've got 12x plus 36 if I distribute that 12. Okay, and that's getting multiplied by the quantity 4x minus 1 squared. And I'm subtracting the quantity 4x minus 1 cubed. And this is all going to be over x plus 3 squared. And so maybe I factor out 4x minus 1 squared. That'll make this look a little bit different. So let's do that. Let's factor out the 4x minus 1 all squared. And so I would be left with 12x plus 36. And then I've got one factor of 4x minus 1 left, since I factored out 2 of those. Rewrite my denominator so I don't lose it. I see that happen a lot on student papers. Don't forget we still have that denominator squared. And so I've got 12x plus 36 here, and it says I can subtract the quantity 4x minus 1. So just do a bit of rewriting here. Distribute that negative. It's a minus 4x plus 1. Rewrite my denominator. And so I could write this as the quantity 4x minus 1 all squared times, and then I combine like terms here. So 12x minus 4x is going to give me an 8x. Then I've got 36 plus 1, so it looks like I'm going to have plus 37. And then I've got my quantity x plus 3 all squared. And so really doing things like I did in these last couple of steps, that's going to be very helpful if I am working on problems that are multiple choice. It's like I know I did my quotient rule correctly, and it doesn't quite look the same. So let's think about all the things that we can possibly do, which is why factoring and being able to combine like terms, adding, subtracting, multiplying polynomials, very important in this class.